All right, welcome to EfficientML.ai Lecture 9 and Lecture 8. We're going to talk about the second part of neural architecture search. So in the last lecture, we talked about the part 1 of neural architecture search, which is basically saying there's no free lunch. We want to get a good architecture that can get a good trade-off between the latency, accuracy, energy, and the storage. In order to achieve that, we talk about those basic operations of building neural nets, classic building blocks, bottleneck layer, inverted bottleneck layer, and also the transformer layers, the introduction to the NAS, including the search space, and how to design the search space, what are the search strategies. And in this lecture, we will start talking about how do we estimate the reward, which is the accuracy estimation. As you can imagine, a good architecture, you want to make sure you can get its accuracy, but accuracy requires training, which is pretty slow and costly. And how do we make it cheaper? So efficiently search the architecture. And also zero-shot NAS. Can we estimate the performance, the accuracy, without training it? Zero-shot, just looking at it. Hardware-aware NAS, how to search an efficient architecture. Make sure the model we find runs fast on the target hardware platform. So this is efficiently search and efficient architecture. Okay, efficiently search and efficient architecture. And we can further open the design space, not only designing the neural architecture, but also the hardware architecture that accelerate the customized neural architecture. So we'll talk about neural hardware architecture co-search. And finally, we're going to wrap up by talking about a bunch of applications that can be accelerated by these NAS algorithms, including the NLP applications, scan models, generative models, this point cloud, widely using ADAS, autonomous driving, pose estimation for human-computer interactions. Okay, so this is the rest of the lecture for today. And we'll start with the accuracy estimation strategy. We've covered the search space, which is the design space in which we are going to search the neural architecture, including the cell level search space and also the network level search space. And this search strategy defines how to explore the search space and how do we sample from the next neural architecture. We can do a simple grid search or a random search, which is basically the starting point we are going to use to do sanity check. We are actually going to do that, try that in the homework, using reinforcement learning, using gradient descent, make latency differentiable, like we talked about in the lecture, how to make latency differentiable. And finally, the evolutionary search, which we are going to implement in lab 3. So in this lecture, we'll focus on given an architecture, how do we quickly estimate the performance, which is the accuracy? We'll cover train from scratch, which is the most naive approach, inherit the weight, using a hypernetwork to save the cost of estimating the accuracy, the performance. And we feed back that performance to the search strategy to update the next sample, the next architecture that we are going to explore. So the basic approach, the most simplest approach is basically train the model from scratch and observe the accuracy. Then we propose an architecture by the controller, and then we train it, update, and obtain the accuracy and update the controller. And the drawback here is it has prohibitive training costs. For example, on Sci-Fi 10, people have to train 12,000 models in order to search for the best one. That is taking 22,000 GPU hours. What if we want to scale it to larger scale data set, like ImageNet, COCO for detection, for classification, etc. So people propose all kinds of lighter weight methods to efficiently search the architecture. So we can inherit the weight. So you have already trained a bunch of stuff, You don't want to throw it away. Previously, every time you're restarting, you're training from scratch. Now we want to inherit from, say, this is already trained model. We can inherit it to make it wider. Right here, you have 2 neurons in this layer. Now you want to have 3. And the way we do that is by a mathematical equal transformation. You can split the parameter f to be half of f and half of f. So you can copy the duplicated node and have 2 copies of that and have the strength for each parameter. So this is net to wider net from this paper. We can also expand the depth by inserting an identity layer. So any layer followed by an identity layer, you put them together, is still the original layer, right? So you can continue training from this model. So every time you are standing on the shoulder of the giants, you're no longer restarting every time by using this neither net to wider net or net to deeper net. So using this approach for the controller, rather than each time we propose a new architecture, the N, C, H, W, different parameters, now the action would be make it wider or make it deeper using the approach in net to net. So we can propose to either net to wider net or net to deeper net. And then we'll continue to train the same set of parameters without having to train it from scratch. So the generator will generate network transformation actions to update the model architecture rather than proposing a completely new model architecture. The next approach would be to train this hypernetwork. So what is a hypernetwork? So that network predicts the weight of the target network. You have a predictor. The predictor's result is the weight of your desired network. Okay, and what is it? What is the predictor based on? It is based on the model's architecture embedding, like the NCHW, the different sizes, etc. So that is not enough. Size is not the only thing, but topology matters. So we want to transform this initial node embedding through a graph neural network. Since the neural network is a computing graph, so graph is a pretty good representation of the neural network architecture. You have the information of your neighbor, your neighbor's neighbor, you have different degrees. And graph neural nets is a very good feature extractor to extract the feature of the neural network architecture. So we pass it through several layers of graph neural net, which transforms the initial architecture embedding into the final architecture embedding. And we use this NLP, which is the hypernetwork, taken the node embedding as a feature to predict the weight of the original neural network. So this network is used to predict the weight of our target network. For example, this is yellow, then associate that with yellow. This is dark blue, then we associate this node with dark blue. This is green, then we associate this node with green. So when we are changing the architecture, what do we change? And what remains the same when we are sampling a new neural network architecture? This hypernetwork remains the same, right? We can update this hypernetwork, but here, when you are proposing a new neural network architecture, the embedding gets changed. The final embedding also gets changed. But we can just train this hypernetwork to predict a new set of weights. So we are sharing the information here rather than train something, throw it away, train something, throw it away. But here we are not throwing away this MLP, this hypernetwork. So we can use the gradient descent to update the weights of that hypernetwork. What if we go to the other extreme, the very extreme? We don't train it at all, by using zero-shot NAS, which is saying, can we estimate the accuracy without even training it? So previously, we try to see if this architecture is good or not. We have to train it on the GPU, train it for quite a while, and then estimate the accuracy. Either wider net to deeper net, sharing the weights, hyperparameter, hypernetwork, whatever you have. You have to train it at least for a while. But zero-shot NAS is basically saying, we just eyeball check, just look at the network, look at different component, without training it at all. Just analyze the architecture without training and estimate the accuracy. And we're going to see two methods, ZenNAS and also GradSci. So what is ZenNAS doing? So it's trying to say, we want to give a little bit of perturbation to the input, and a small perturbation to X to get a new X, okay? And we initialize all the weights to with random number following the normal distribution. And we try to see the difference between the Fx and F/X. If you change the input a little bit, the hypothesis here is that a good model is should be able to amplify this change, should be sensitive about such input perturbation. So you change a little bit, the input a little bit, the output is supposed to change very drastically. This makes some sense, right? You want to distinguish A and B. If you change the input from A to B, the output doesn't change at all. This may not be a good model. Question here.
I have one question about this is that what about small perturbations like adversarial ones, where a little bit change should not change the model output, but in this case the model is sensitive.
Right. Therefore, we try to. There's a second term, right? The first term may not be enough. The model might have very drastic change no matter what the input is. That is not stable, not robust. So this method is adding a second term, which the batch normalization variance. So what does batch normalization do? It's try to flatten, to stabilize the distribution of the output feature map across different inputs. Right? So it try to compensate for the first term by adding the batch normalization variance, which is calculated in this way. And finally, we have the sense for to be the perturbation plus the variance of the batch normalization layer. But this covers some of the intuition, but it still is a heuristic. There still might be some other adversarial methods that might be able to attack this approach. So as you can imagine, that totally makes sense. We don't train it at all, but you want to get the accuracy. That's not quite reasonable to begin with. If everything is 100% accurate, then we don't have to train neural network at all. Right? So this is just some of the heuristics that might be able to offer you some kind of insight, at least help you eliminate some of the incorrect models. For example, if a model, the input changed from A to B, but the output doesn't change at all. Then we are almost certain this may not be a good architecture. The input changed, but the output remains the same, right? So, so good model should be sensitive to input perturbations, but it's not saying if the model is sensitive to input perturbations, that is certainly a good model. All right. So another intuition is that if a model is pretty good, the distance between the local minima, two different local minima, should be closer. There's a higher probability that the gradients of different samples have the same sign. Like here, these two local minima are pretty far away. But for this one, the local minima are closer. If that is the case, the sign of the gradient of different samples should have the same sign. Like here versus here, you can find that the direction of the gradient is different. So we are just sampling, have a for loop over all the samples, okay, different inputs, and then sample and loop over different layers. And for different layer, we add up all the gradients corresponding to the sample I in layer K. And if they have the same sign, this number is supposed to be larger. If everything has the same sign, either positive or negative, the largest value could be n. But if I have 1, -1, 1, -1, all the signs are different, this number will be 0. So it's a for all the layers, for all the samples, if you sum up across different samples, the sign of the gradient should be consistent. Okay, so those are some of the performance estimation methods. So that only give you part of the story, right? Which is the accuracy. But accuracy is not all we want. We want the model to be small, to run fast. So we need to make it hardware aware, to have not only accuracy information, but also the latency, the energy, the other hardware related information. For example, one approach, we can assume ideally a good model that can fit different hardware platforms. If it's a general purpose model, it might be inefficient because different hardware platforms prefer different kind of computing. Like GPU has pretty large parallelism. If you increase the channel by doubling it, twice as the channel number, it may not change the latency at all if you are not saturating the number of tensor cores. But Raspberry Pi may have much smaller amount of memory. So if your model size can barely fit the SRAM versus just increase by even like 1 kilobyte, it's not going to fit the cache. The performance may be drastically different. High-end CPU, low-end CPU, they all have different size of the cache, right? So here, specialization is a very good approach to improve the efficiency. You want to have a specialized model for the Pi, specialized model for the GPU, specialized for the model for the CPU, for mobile, etc. But what is the overhead here? The design cost, right? Previously, you just design one model rather than 50. That's it, good accuracy. But now you may have to design a lot of models, train them individually. That's pretty costly. And let's see how do we solve that. So let's first review what happened before. As we talk about previous neural architecture search used to be very expensive. Things you gotta train a model, get the accuracy. If it is not good, train again, get the accuracy. Takes 48,000 GPU hours on Cypher, not to mention ImageNet. Single GPU, that's 5 years. Google has lots of GPUs, so that's not an issue, but that's definitely an issue for us. So previous work has to utilize all kinds of proxy tasks, like train on Cypher and then try to generalize on ImageNet using a small architecture space, like very few depth, and repeat the block, assume it works well for different depths. Or just do a couple of epochs of training, say converge it at 90 epochs, and just train a couple of epochs to test drive the accuracy. What is the problem here?
Yeah, the model might not converge in accuracy because it is possible that gradient for the loss confidence and bound, the accuracy might have been much better if we allowed it to train.
Right, exactly. since the model may converge super fast in the beginning, but later is doesn't have any potential, or a model may not train very fast in the beginning, but later the loss begins to drop very fast. So that's the problem for few epochs of training compared with training to convergence. And also using flops and parameter count as a feedback for latency. But as we have seen numerous times, flops and parameter count doesn't always reflect the latency and the efficiency. So here, we propose a technique called proxyless NAS. So rather than relying on this proxy task, small data set as a proxy, small architecture search as a proxy, fewer number of epochs as a proxy, or flop parameter as a proxy. Now we want to truly train it on ImageNet, unlock all the layers, directly search them, and also use the latency rather than the flops as the feedback. How do we achieve that? We first build a over-parameterized network. It can contain many different choices, much wider, much deeper. You may not want to use it in the end, but now we give you this opportunity to choose between different kinds of layers, like 3x3 count, 5x5, identity, coding, whatever you have. We have everything in the design space. So it's an over-parameterized network with all the candidate paths. This is one path, another path, all the different paths. And we want to simplify NAS to have a single training process compared with you train a model, evaluate the accuracy, train the model again, evaluate the accuracy, train another model, many training iterations. But now we want to simplify it to be a single training process of this over-parameterized network. And such network has two kinds of parameters. One is the weight parameters. That's just the weight we talk about. The other is the architectural parameters, which defines the architecture. Like if we are choosing this branch, this path, this is the probability of choosing a certain weight parameter. Okay, so that is the architectural parameter. So actually, we can quantify the architecture by the probability of choosing different paths. And this is the binarized version of the architectural parameter. Only one of them should be 1. So we can iteratively update the weight parameters and also the architectural parameters iteratively. Question here.
So are you saying that we would have weights for every prospective architecture?
We have weight for each building block, each path, and you can repeat this layer many times, or you can have this architecture for different layers. This is just one of them.
The architecture parameter determine the architecture of that layer?
The architectural parameter is the probability, like among these 4 choices, what is the probability of you should choose this block? Okay, so in this way, one iteration, we update the weight parameters. Which one do we update? That is sampled according to the architectural parameter, which is the probability of choosing this path. Like this path has the highest probability, or this one has lower, then it's still possible we sample this path, just the probability is lower. And in the next iteration, we update the architecture parameters to update the alpha beta probability. And finally, in the inference time, we can sample the largest probability, okay, and prune those redundant paths based on those architecture parameters. And we binarize the architecture to allow only one path of the activation to be active in memory. Otherwise, you have to keep all the different choices in the memory. Right? Previously, one layer you have one convolution, but now you have 4 convolutions that will explode the memory. And therefore, we can remain we can keep the memory footprint from ON to just O1. So in this way, rather than relying on a proxy task and then transfer to the target task in target hardware, we can directly learn the architecture of the target task in target hardware. For example, not on relying on proxy task on Cypher, but directly use a target task ImageNet. Not relying on small architecture search space, but directly open up the larger architecture search space. Rather than using few epochs of training as a proxy, but enable full training. Rather than relying on the flops as a proxy, we can profile the latency. So this is one example we have witnessed about the max doesn't translate directly to the latency. For example, here, comparing this point and the point right here, this point has fewer number of max, right? Compared with this blue dot. This is the NASNet. This is the mobile net. Although NASNet has fewer number of max, you still remember MAC. That's multiply and accumulation. Although NASNet has fewer number of max, it actually has much longer latency, from 140 something milliseconds to 180 milliseconds, right? So those conventional NAS methods have similar max compared with human design, but actually higher latency. Another phenomenon here is that when we are scaling the hidden dimension versus the number of layers, this is the same starting point. When we are expanding the width of the neural network and measure the latency on the GPU, it actually doesn't quite increase because the GPU has such large parallelism, such that even if you are increasing the workload, increasing the channel, it doesn't quite increase the latency. But if you increase the depth dimension, the latency is going to increase very proportionally. So which is showing the flops versus the latency is not linear. Like these 2 points, they have very similar flops, but drastically different latency. So latency and flops is not good representation for the latency. This is another example. Although GPU, the latency is not quite influenced by the hidden dimension. The increase in the hidden dimension doesn't quite change the latency, but Raspberry Pi is very sensitive. Has very limited parallelism. We increase the flops a little bit by increasing the hidden dimension size, the latency drastically immediately increase. So the latency feedback becomes super crucial. We have talked about the accuracy measurement, the accuracy feedback. What about the latency feedback? One naive approach, certainly we can measure the latency directly. What is the drawback here? To directly measure the latency and feed it back to the neural architecture search loop. Very slow, right? It can be very slow. It's manual, it's very slow. And also it can get heated, get hot. And it can slow down the inference. One approach is certainly we can build a latency model to predict the latency by first collecting a latency data set. The feature, the input is the architecture representation. The output is the latency. Given the architecture, predict the latency. So there are several approaches. We can first do the layer-wise latency profiling. Like a neural network consists of many different layers, and there are finite number of choices in different layers. You can probably choose between 3 and 5 as kernel size. And for the width, you can choose from 64 to 1K, step size of 64. You can choose resolution, etc. So each layer, there is finite choice. We can pre-allocate, we can pre-compute, pre-measure the latency of each choice and build a lookup table. And what is we are assuming here? We are assuming for different layer, the latency is basically the sum of different layer. Like latency of 10 layer neural network is the latency of layer 1 plus the latency of layer 2 plus the latency of layer 3. They're addable, and that's indeed the case. However, not all the case. That's not the true for all the case. There are different scheduling we can do, including the patch-based inference approach, which we worked on in NeurIPS 2021. We are directly inferencing partially for several layers altogether. So it may not be addable, which is a KPI here. A more general approach is that we can build a latency data set. Okay, so the architecture, operator 1, latency, operator 2, latency, etc. So when we are building this is still about the lookup table. So the lookup table is basically operation 1, latency, operation 2, latency. We collect a very long list of operation versus latency, operation of latency. But this is still finite. You have a few choices of the kernel size, a few choices of the input channel, a few choices of the output channel, and a few choices of resolution. Multiply them together and just do measurement once. So this is showing actually using the latency lookup table, we can get a pretty accurate predicted this is the real measured latency versus the predicted latency, very close to y equal to x. And the other approach is basically build a more general predictor. Given the architecture, predict the latency. And what are the features when you are trying to predict? So you can include the kernel size, the width, the resolution, basically all the hyperparameters. And we use several layers of MLP, fully connected layer, to output a single number, which is a predicted latency. You can certainly make this more complicated, like using the graph neural nets we first talked about in the early part of this lecture, to encode, to extract the feature of this neural net, and then predict its accuracy. Its latency. Actually, such a predictor can work quite well. So this is in HAT, hardware-aware transformer. This is the predicted latency. This is the real latency. And for transformer architecture, it's very close to y equal to x. So we can use the predictor to estimate the latency rather than physically deploying this model on the hardware and run it. So in that way, we can find specialized models by incorporating both the latency measurement and also the accuracy measurement very quickly. So by combining this together, we can outperform this human design mobile V2 by running 80% faster. And we can design specialized model for the CPU, for the GPU, for the mobile. Interestingly, this is has a diagonal pattern where the model is designed for the GPU, works the fastest on the GPU platform. The model designed on the CPU works the fastest on the CPU. And the model specialized for the mobile works the fastest on the mobile device, which makes sense. And let's see, how does the search model differ across different platforms? So this is the history of finding an efficient model using proxy NAS for the mobile phone versus finding a specialized model for the CPU versus the GPU. What do you observe here? especially for the GPU model. It's consistently shallower than these models, right? And also it's wider. Aggressively chose this 7x7 convolution, which is in red compared with 3x3 in blue. Since the GPU has a larger parallelism, I prefer to do more in one single layer compared with doing more layers, okay? Which makes sense for the parallelism. All right, so far we talked about this kind of specialization for individual hardware platforms. But in real world, when you design a neural network, you want to deploy it on different scenarios, on the edge, on the cloud, on Apple mobile phone, and also on Android phones. So how do we save the search costs for diverse hardware platforms? Let's take a break and we'll continue talking about that in 5 minutes. Resume our discussion for multiple hardware platforms. Assume we just have one device, like a brand new iPhone. If you are doing the conventional search methods, we want to search a couple of episodes, and each episode we want to train a model for several iterations to do the forward and backward and get accuracy. If it is a good model, then we break. Otherwise, we continue the search process, train another model. Okay, and finally, after the training, we find a good model. Then we are going to fine tune it a little bit to get a final accuracy. Right? We are going to repeat this process many times. And this is the design cost. I mean, certainly, if you're an app developer, you want to do a startup, you want to have something on Apple App Store. You certainly want to support not only 2023, but also some older phones, okay? And try to be inclusive for users who not only for users who have newer phones, but also users who have outdated phones to be inclusive. So immediately you have to increase the search costs by finding good models for diverse devices, and that will just explode if you have many different devices, from cloud AI to mobile AI to tiny AI. And also another problem is that existing models are very heavily optimized for the GPUs, but doesn't well fit other platforms. There are also other hardware platforms like TPUs, the DSPs, different kinds of accelerators. And how do we improve our productivity so that we can enable a turnkey solution, push the button solution for people to easily find the best fit neural network architecture across diverse hardware platforms. So here is a proposed approach. Compared with the other conventional approach, every time we have to train a network, get the accuracy and latency, okay, train for a day. If the accuracy and latency matches satisfying, then we keep it. Otherwise, we have to resample again. We repeat this many, many times. Each time we require a long time to train. A natural thinking is that, can we amortize this training time? We can just train only once, okay? But after this one-time training, we can get different subnetworks, many, many different subnetworks. We can have a bigger subnet, smaller subnet, a mid subnetwork. We just select our target architecture from this once-for-all approach. We just sample a smaller subset of the weights and make it into a new neural network. And we have to prevent different kind of smaller neural networks from interfering with each other so they can independently operate. And we select a subnetwork, get the accuracy and latency. If it's satisfying, then we are good. If it is not satisfying, we sample another subnetwork and measure the latency and accuracy. The second time, we don't have to train it, but we directly use the weight from this once-for-all network. Yeah. Okay. So you pay one-time overhead to do all the work in the beginning to train this once-for-all network, and in the future time, you just need to sample a subnetwork. So the key idea is to train once and get many to reduce the design cost, so that we can get a larger subnetwork for newer hardware platforms like the Agent 1, a smaller subnetwork for weaker, for older, less powerful platform like Qualcomm 855.
Essentially a random search for post-training.
Post-training, yes.
And when you say sample, is that uniformly or is it weighted by something like
Uniformly, random sample. Random sample. We are going to try that in the homework. And of course, you don't have to do random sample. You can certainly do that as a sanity check. Make sure after a few times of random sample, your results are getting better, to do a first order sanity check. And after that, we'll actually implement an evolutionary algorithm to improve the sample efficiency. You are going to implement crossover, the mutation, with a smarter way to select a good subnetwork. An amazing part is that you share the same once-for-all network, so you don't have to train it. That's why you can complete that in the Google Colab. So we have carefully designed the homework so that you can finish within the budget of Google Colab. We tried really hard for lab 1, 2, 3, but for lab 4, that is impossible without having to pay Google $10 per month. We did try our best, but please, you want to complete lab 4 for compressing large language model. We have to use the advanced version, the paid version, $10 version for lab 4. But up to lab 3, this method is just so efficient, you can just complete it with a free version. Or we can use a larger network for larger memory, like 12 kilobyte to memory, 12 kilobyte of SRAM, 2 megabyte of flash, versus the smaller one, we use 256 kilobyte of SRAM and 1 megabyte of flash. Newer phones, older phones, full battery case, battery saving mode in the morning and night. Right? So make sure you develop an app, you can fit different scenarios.
When you talk about some of the without retraining, the accuracy goes down. Do we expect the accuracy to be for all these subnetworks?
Yeah, these subnetworks, you want to retrain it after you search it to get the best accuracy. That's why we have the follow here for post-search training iterations to fine-tune the model to fully get the best accuracy. It was on MIT News a couple 3 years ago. So design new efficient models rather than compressing existing models. Just train once, get many, reduce the search cost. Actually, we can have 10 to the 19th subnetworks trained at the same time. You can get many different child networks for free. The key idea is the child network share the weights, so they don't have to be trained individually with the once-for-all network. They train jointly and amortize the training cost. So how do we make it possible to train such a once-for-all network? For example, a larger model may have 7x7 kernel, middle one 5x5, smaller one 3x3. How do they efficiently share the weight? We can have a 3x3 model inside this 7x7, and 5x5 inside 7x7, and 3x3 inside this 5x5. And just pass through a MLP that project this 25 to this 25 weights, which is a very smart way. Or similarly for the number of layers, we can progressively shrink the number of layers while we are doing training. We can first train with full depth and then shrink the depth. Now we can select either these 4 layers or these 3 layers. We can randomly sample different choices at training time. And finally, we can continue to shrink either 4 layers or 3 layers for only 2 layers. So this is progressively shrinking the number of layers. We can also progressively shrink the number of channels. Like this is the full width. And also we can sort the channel importance based on the L2, L1 or L2 norm, similar to channel pruning. And then we can either just use 3 channels or use 4 channels. The next iteration, we can use either 4 channels or 3 channels or 4 channels. So we are progressively reducing the kernel size, progressively reducing the layer number, and also the channel number.
Can you please explain how you're reducing the layers work? So would you just pass through in O3, you just take the output from the green layer and ignore layers?
You ignore these 2 layers. And you can, at different training iteration, you can sample different paths randomly. Like here, you have 1/3 of the probability just go through only 2 layers. 1/3 of the probability just go to O2, or 1/3 go to O1.
So the dimensions are all the same?
The dimensions are certainly the same.
And
This is within the same resolution, the same stage. So the dimension O1, O2, O3 are the same. Just difference is only they pass through different number of layers.
so it's still not quite the same with actually training that subnetwork, right?
At the training time, you are not training a fixed network. Like here, we're showing the animation. Different iterations, we are training different part of the network. That's the key difference. And actually, recently, if you see the rumor about GPT-4, one of the key techniques they use is the mixture of expert, which is sharing some similar taste as this way. It's sparsely activated. Not everything is activated, but sparsely activated, both during the training time and also during the test time.
So it's not quite an ensemble model, but is it fair to think of it sort of as like an ensemble across time rather than every prediction?
Yes, that's the right analogy. Ensemble, different networks together. So this is put it in another way to visualize it. I made a very good-looking slide to show you elastic resolution, starting with bigger resolution to smaller resolution, and then from full kernel size to partial kernel size, 7x7 to 3x3, progressively shrink it, and the depth progressively shrink it from 4 to 2, and also progressive shrinking for the width from 4 to 2. Okay, this we call it elastic resolution, elastic kernel size, because you can choose either a larger one or a smaller one is elastic. So let's see how does it perform. This is the roofline analysis. So the x-axis of the roofline analysis is the operations per byte. Like fetch 1 byte of data, how many operations, how many multiplication add we can perform on top of that byte. That is operations per byte, which is also called arithmetic intensity. How intense are we going to do a lot of operation on top of 1 byte, or just do a little bit of operation on top of 1 byte? Okay, larger is better or smaller is better? Remember, data movement is expensive. Computation is cheap. You fetch 1 byte of data. You want to do as much operation as possible on top of it to amortize this data fetch overhead. Right? So we ideally want a larger ops per byte from the application's perspective. On the y-axis is the measured g-ops per second, how many giga operations you can do in each second. Initially, this is linear growing. And finally, it's going to peak. It's going to get peaked at the peak operations per second of your hardware. For example, if it is 20 teraops per second, that's the peak performance of the processor, then this is the roofline. And before that, when you are increasing the operations per byte, you are bounded by the memory bandwidth. you have a fixed amount of memory bandwidth. The compute is not saturated. So as you bring up the operations per byte, you fetch the same amount of byte. Now you can do more operations per second. Right? So here we are memory bounded. Here we are compute bounded. And the higher the better, the higher the utilization.
When you say multiple operations per byte, that would manifest here as sampling many subnetworks for the same set of data points for the same batch. Or is it?
Oh, this is much lower level, right? So for a given neural network, you fetch some weight, fetch some activation, you do some compute on top of it.
I see.
Yeah, that's much lower level of definition. And we can see this is MNOSNet, MobileNet V2, roughly here. But the search, the one-for-all network, the subnetwork specialized for this FPGA actually have higher arithmetic intensity and also the higher measured GOPS per second. Although we didn't explicitly teach it, but you need to search a model that has higher arithmetic intensity. It automatically finds that by feeding it with the latency feedback. So which is very interesting as an end-to-end learning process. So here is the ZU3 FPGA GOPS per second, comparing MobileNet and MNOSNet versus OFA with respect to the GOPS per second. So if you have a Raspberry Pi, you want to deploy some neural nets on it, highly recommend to use one-for-all network to find a specialized model for that, because MobileNet V2 and MNOSNet, neither of them are specialized for this particular FPGA device. Not only on one device, but also Wi-Fi works quite well on diverse hardware platforms, different phones, Samsung phone, Google phone, LG phone, GPU, CPU, and also FPGAs like on the GPU. This was still using 1080 Ti because this project was like 4 years ago. Same 72.6 top one. This is top one accuracy. I was a little surprised because these days we are talking about 85 top one accuracy. Only after 4 years, things have so much improvement has been made. With the same 72% top one accuracy, the latency gets reduced from 28 milliseconds to only about 12 milliseconds. Pretty amazing speed up. What's next? We search the good neural network architecture. Can we co-design the accelerator architecture for full stack design? As the Moore's law is slowing down, we are no longer having a free lunch provided by the nanotechnology, right? So there's plenty of room at the top by co-designing the algorithm with the hardware architecture. So here we'll work on this neural accelerator architecture search, NAAS, to search both the neural architecture and also the accelerator architecture. Hardware side, the software side, continue this loop. Okay? So this neural architecture, accelerator architecture, visualization. And what are the design space? What is the key dimensions in design space? We can break it down into 3 levels of hierarchy, from the hardware part to the software part, with compiler in the middle. On the hardware part, we have the buffer size, local buffer size, global buffer size, the number of PEs, and also compute array size, the connectivity. The compiler side, we have the loop order, the loop timing size, how do we tell the loop, what is the data flow. On the neural network side, we have the number of layers, number of channels, kernel size, whether we have bypass, what is the quantization precision. And we want to jointly search in one optimization loop, right? To open up a much larger design space compared with only doing neural architecture search. But now we're also working on the accelerator architecture search. The design space can be roughly categorized into two types. One is sizing related. The other is the connectivity related. Sizing related is very easy to search because they are numerical values. You just search a number and just assign the number to it. But what about this connectivity parameters? They are non-numerical. For example, we have the loop tidying strategy. We have the loop order, okay? 1, 2, 3 or 3, 2, 1. We have to take care of the hardware parallelism to choose which for loop do we serialize in time versus parallelize in space. Okay, parallelize in space means you have multiple PDs, means you have the parallel for doing them concurrently. Serialize in time means that you have the for loop in the time dimension. Okay, so there is temporal mapping. There's also the spatial mapping, and those non-numerical architectural parameters is the key we want to solve here, because you cannot just make it into a classification or regression problem, because this is choosing one or two dimensions, several dimensions among different choices. This is ordering several dimensions. It's not a classic classification problem, nor regression problem. How do we deal with that? We use index. One approach, certainly we can use index-based encoding. Right? This is one possible loop order. We assign it with the value index. Another possible order we assign with a possible loop index. But the problem is that the index value 0 or 1, 1 is larger than 0, 2 is larger than 1, but will not necessarily convey any physical information. Like why this is larger than this, that doesn't quite make sense. This is just a symbol rather than a number, not the integer, not a real number. So the increment or decrement of index doesn't convey physical information. So rather than that, we use this importance-based encoding. Okay? Since the importance can be represented by numerical number. Say here, we have 6 choices of the dimension we can parallelize in space. Which dimension do we choose? We can learn the importance, relative importance of these different dimensions and just rank it, and then sort it by picking the top k of them. Say we have, we can afford to parallelize 2 dimensions in space. We just find the most important 2. Okay? We can assign the importance, which dimension we are going to parallelize, and then we are going to learn it, update it, and finally when it converges, we sort it and pick the top k dimensions that we can parallelize in space. Similarly, for the loop order, we learn the importance of each loop. Since for these important loops, we want to put them in the outermost, since it is it's going to have the least amount of iterations, versus those less important loops, we want to put it in the inner loop, which is going to be super hot, looped every time, assuming that's cheaper and not important. Okay? So in this way, we can actually turn those non-numerical hyperparameters into numerical hyperparameters, so that we can learn as soon as they become like integers or real numbers, we can learn them. So together with those numerical parameters like the sizes and the tidying sizes, which is easily represented, and also the number of dimensions, etc., they are all numerical value. So this is the purple part about the blocking, the size of the block, and also these non-numerical values, which ones will be parallelized in space. So these are parallel forms from C and K, and here is the order that we put from the outermost to the innermost. So we can do this joint search for this neural network design space. This is the population for the mapping for the compiler, and also in the inner loop, that is the accelerator. Okay. And how does it compare with architectural sizing only. Sizing means we only search those numerical values like the cache size. Actually, a big improvement when we have the luxury to search not only the numerical architectural sizing only versus searching the connectivity parameters as well. And this is comparison with the starting point, which is a baseline human design, which is basically less than 50. This is the normalized energy delay product. So by applying this hardware architecture search only without changing the neural network architecture, about 4.4x energy delay product reduction. And by searching the neural network architecture code together using the once-for-all NAS, since every time you're proposing a new neural network hardware architecture, you have to search a new neural network with diverse hardware platforms. Now, once-for-all network came into play. And 2.7% accuracy improvement. And to actually search NAS design data flow designed to parallelize the output height and output channel dimension. And this is the buffer size it shows, 496 byte, which is quite different from human design. So that's all for the neural architecture and hardware-aware neural architecture search. Now we're going to switch gear to talk about some applications. How do we accelerate real-world applications with NAS, in particular with the once-for-all approach? First, transformers. So far, we talked a lot about CNN models. What about transformers? So this work is expanding the once-for-all network to transformers. So we first train this once-for-all transformer and then derive different sub-transformers by weight sharing. We can use a smaller transformer for IoT device, a larger transformer, wider transformer for GPU, deeper and shallower and narrower transformer for the CPU. Compared with the evolved transformer, the HAT hardware-aware transformer, you get much better latency and model size while preserving the accuracy. You can run on Raspberry Pi, and also GPU have specialized model for different hardware platforms. And also we can apply this once-for-all approach for point cloud. You know, point cloud is pretty sparse. It captures the spatial information in the 3D world. So previously we have talked about 2D vision, but this is 3D vision. Very crucial for ADAS, autonomous driving applications. We certainly want to run it at fast frame rate. This is latency critical, safety critical. Understand the surroundings at higher frame rate. So here, for the point cloud, we made this SPV NAS sparse point voxel neural architecture search. So here, we train this super network with different stages. We can choose from 3 full depth, partial depth, or even smaller amount of depth from 3 to 3 and 1 to 3. Okay, so progressively shrinking the depth, and also we can progressively shrink the width. So this channel input, channel output, we can support these 2 dimensions. So you support elastic channel number and also elastic depth. So we get a super network, sample a sub network. We test the latency and accuracy. If it doesn't meet our target, we have to propose another candidate network and repeat this process. The super network remains unchanged. You pay the overhead only once. And we search using the evolutionary strategy, which we are going to implement in our homework for lab 3. We do the mutation. This layer we change the number of channels. And also we do the crossover, get the gene from both parents, part from parent 1 and part from parent 2. Okay, we are going to implement that in our homework. And finally, select the best fit and continue to get the next generation. And this is a demo comparing the CNAT 3 and 4 2.4 frames per second versus XPD NAS 9.1 frames per second, very much faster. And this is once for all for GANs, generative models. Generative model used to be pretty compute intensive. Like we can make her look younger, but it takes about 3 seconds. Pretty slow. It's computationally heavy, but we want to make it possible to run interactive photo editing locally on our edge devices, like on an iPad. Right. So how do we make it fast? So the difference here is that the generative model not only have just one model, but it has a discriminator and also a generator, right? So we train once, we train generator only once, we make the generator to be once for all. And then we can select a small subnetwork at low cost, very fast prototyping. We can just scroll it, immediately see what is the effect. Okay, we change the hair color, immediately see the response, and click the finalize button. What we are doing here is actually it's running this largest full model, okay, which gives you the best quality result with slightly longer time, which is affordable because you do it only once. And here is another example. Usually getting older is associated with wearing eyeglasses. So that makes sense. So we can in this bar to the left to remove the eyeglasses. After everything is done, finalize, which is running this full network, slower, higher quality. If we have the one last example. It's immediate. Everything is open source. Feel free to check out NCalScan and can run it actually locally on a laptop, MacBook. This was in 2021. I believe the MacBook is much stronger these days than 2 years ago.
So all of the different models are trained offline once, and then they're downloaded with some update to the iPad or whatever.
Exactly.
So this is all inference. This is only inference.
Exactly. Yes. All inference time. And another good point, compared with larger model, smaller model, you may have to download many different versions of the model. Big model, small model, many models. But now you can just download one model and then at runtime decide whether I need to run a smaller one or a larger one, or seamlessly get a trade-off. Yep.
Is the whole model loaded into memory when you do inference, or just the subnetwork?
Just the subnetworks. Just the subnetwork.
And actually, in this use case of thinking about the actual use case, the main value is actually the fact that it's more of a storage play, right? Because the actual training of the model happens very rarely. So the savings there are maybe less important in this example. And it's more the fact that we're only to store one model on your memory device.
Correct. The training time is actually longer than just train one model. The training time is about 2 to 3 times the original training time. So the training time is actually longer. The whole purpose is to make the runtime, the inference time more efficient. And another insight is that this model obtained from this once-for-all network actually outperform the same architecture trained from scratch. That's a very interesting phenomenon. This small model is even better than the model itself trained from scratch. We suspect that is due to the regularization where the same set of weight not only have to work with itself, but also have to work when it acts as a subnetwork as another network. And the weight sharing are learning together, making it more generalizable. Lots of things remains to be analyzed. Very interesting phenomenon. So, and we also suspect this kind of over-parameterization can sometimes help with the training of smaller network.
So each subnet is fine-tuned, right? And then How does it affect the accuracy of the largest model?
So if you are determined just using one particular subnetwork, you have to fine-tune that. But in this case, we want to run both the larger model on different subnetworks. In this case, we didn't fine-tune them. We just directly use the sampled subnetwork to run inference. Still works super well. That is showing the effect. Well, only when you are pretty sure you are going to build ASIC, you want to just run this model, then you can fine-tune it irrespective of other components. And finally, for pose estimation, again, we train this one small model, then get the subnetworks with a single path. We actually find just one single path works quite well. It's the latency, accuracy, MAP trade-off, actually about 5x latency reduction. So that you can build such real-time pose estimation, multi-person pose estimation for activity recognition and other estimations. So actually last semester, one of the students used this demo. She's on the rowing team and build a trainer app using this tool, which is quite interesting to distinguish the different positions when she's doing the rowing of the training. This could be one of the final projects. We have a couple of such Android phones in our lab. So if you decided to build a final project on a mobile Android device, we can borrow you a phone. Here are more examples for lightweight detection, gaze estimation, and segmentation. Another interesting part is once for network also get applied to quantum AI, which we're going to cover a little bit in the later part of this lecture. So not necessarily if you have more number of qubits, that's not necessarily a good thing because give you larger capacity, but also a lot of noise. So here you're showing this is the ideal case versus the measured case. The noise-free simulation versus the measured result on the IBM Yorktown quantum machine. The only four classes, administrative 4 accuracy, actually there's a big gap between the simulated accuracy versus the measured accuracy. And actually, the gap is due to the noise. Okay? So the topology of a quantum circuit matters. Not necessarily we put more qubit, we get good accuracy. So here we can train a parameterized super circuit. Okay? We can have different choices, but we put everything in our design space and train the super circuit. And each time we sample a sub-circuit, each rectangle here is a gate. It can be either there or not there. So we can sample different sub-circuits and finally search the best one. And here is comparing with the baseline. And this is our measured result, which is accuracy on least 4, classified in 4 digits. This is measured on real quantum computer, real QC, getting a much better accuracy from 40-something% to 80-something%. Take home is that quantum noise is the bottleneck. For quantum neural nets, big degradation about accuracy. And quantum NAS, quantum noise-aware search for robust circuit, basically train a super circuit and then search a sub-circuit that is robust to the noise and prune away those small magnitude quantum gates. So pruning also applies over there. If a gate is not necessary, it may incurs noise, so it may as well just to prune it away. And we build this torch quantum library, which is also open source. All right, so that's all for today's lecture. We covered hardware-aware NAS, how to efficiently search efficient neural network architectures, the zero-shot heuristics, how neural hardware architecture co-search, and several applications. In the next lecture, we are going to talk about a new chapter, which is knowledge distillation. All right, thank you.